what are the concepts that are in the electromagnetic field theory. And I think I haven't discussed about transmission line theory in detail. Maybe in the course of time we will go for that. So the concept of electromagnetic field theory is very essential in daily life. That is what we have concluded, and for that we need important mathematical descriptions in terms of the direction and the change, whatever that is happening inside the system in terms of the fields or potentials like that. So for this mathematical description is uh, very much needed, and it was evolved exactly in the time of electromagnetic field theory itself. At the end of the 17th century, they have come up with important concepts, including the theory of relativity, all which evolved almost in the end of 17th century itself by Pointer. So, uh, so at that time only this all vector, the vector algebra, vector calculus, all these things were evolved. So as I already mentioned, this is not available in your syllabus. So you may not get the questions for this vector calculus, all these things in the exam, but it will be asked mostly in terms of the physical quantities like electric and magnetic fields. So actually, I always request students to learn this, take this particular book, The Elements of Electromagnetics by Matthew Sedicu. It's a very excellent book. First three chapter covers this, all the fundamentals of the vector calculus and coordinate system all the way. So I always insist all of you should go through that first. Once you have, when at least you just take some hands-on training on various calculations on using this Tel operators and conversion from one coordinate system another coordinate system. So without that, when you directly go to the exam, you will be feeling very much weird about that. So anyway, we will on the course of time we will do some several exercise. Yeah, we already know that why this EM field theory requires this vector calculus, all these things. The very important reason is between two places, the electric field may be different, and if they are different, then always there will be a introduction of the potential difference will come. That what makes the electron flow or heat flow, many things happening because of that. So this all flow change and the projection, all these things supposed to be estimated through directions. So that is why we need vector calculus. For that, we have moved to what is scalar vector and unit vector. And then we also have seen how to multiply the vectors. If these vectors are same type and if the vectors are orthogonal to each other, how to do the multiplication, all these things discussed. And these vectors will be mapped inside the scalar quantities. So when the this Cartesian and other coordinate system will come into the picture, there comes uh, the all type of shapes, everything will be evolving in that. So within the shape, the direction will come into the picture. So that tells the flow of fields or the flow of let's say some the gradient or whatever the vectorial concepts, whenever they flow through a body or a shape. So how to estimate that? So for that, we need this coordinate system, and depends on the application, this shapes and as well as the particularly the application will decide that what coordinate system we supposed to use. Now, one of the very important one is the spherical coordinate system. In fact, most of the charts related studies and antenna related studies are done with spherical coordinate system. On the other hand, this microengineering as well as transfer line theory, they need mostly rectangle coordinate system and cylindrical coordinate system. Kind of transformations, all these things, you could see this example. This week itself, I will upload all the slides. So you can download and you can see yourself and you can solve some of these problems. First, you take this problem and work out in the same way, and check whether your calculations or your way of uh, calculating in the calculator is you are doing correct or not. So first you have to cross check that. Sometimes you have to change with different modes also to calculate the angle all the way. When you directly calculate that, you won't get in angle. You will get always in radians. So you have to multiply with 180 by pi to get it in degrees. So these kind of concepts, we should be well aware of that. Some people will come to the exam and they will, instead of writing the exam, they will do research in the calculator. And I found there are some very interesting people that they will buy exactly one day before the, particularly the calculator, they will buy one day before the exam, such that they are going to use everything new for the exam. But unfortunately, that calculator might be having different operations rather than you have practiced with. So these kind of simple things you have to be a bit careful about. And one more advice when you do this kind of workout, that always calculate, let's say you are calculating this root of x square plus y square plus z square. So what people used to do, yeah, I know this value. This is 2. Then I know that it is 4. This is 6. Therefore, I will get 36. This is 3. Therefore, I will get 9. Then they will also manually add. So it will give 49. So root of that 7 will come. So these people, I call them as Ramanujams. So they generally do everything else in that and they will work out, yeah, like that. But what these people will do is they will once again calculate this root of x square plus y square again. But if you have done this individually, like this, how Sadiku has done, Sadiku is one of the great mathematicians. Even I have seen his lectures as well. So, but he always insists that do always like. So when you do this, you will get immediately the values. And so this kind of step-by-step procedure, when you do, even some mistakes comes, we can give marks. So don't do Ramanuja method. So why I'm saying Ramanuja method means Ramanujam always he will always mentally he will calculate and say that left hand side equal to right hand side. Like that he always write. So that is the problem with him. But whatever the equations he has written, mostly 99% they are all correct. So still people are cracking that he came up with 6 intelligent equations, which often referred as Mach theta functions. So people have solved only 3 out of them. So still 3 is pending. So I think people are saying that it will take another 5 years to solve that. So don't do such method. Okay. So and because I can't give marks, if you directly give the answer, right or wrong, that's not a matter. The flow is very important. So I will always give marks for only for the flow. This flow, if it takes time, then you should know how to solve as quick as possible within the given time of examination. So this kind of matrix, many people sometimes want to draw this, means write this matrix. Directly they will apply, they will go ahead with that. So any one of the method you have to flow, you have to work out. And of course, in case of this calculations, this sine theta, cos phi, cos theta, sine phi, all these things, if you calculate and keep it in the rough work side itself, then it will be very easy to apply all these things and you can easily get the answers. Some many problems discussed in Sediki book itself. You try to do that. Next, we have come to the very important concept, that is differential calculus. So this differential calculus is, we know that it is introduced by famous scientist Newton. Um, then people have evolved out of that. They have come up with several differential equations and solving methods and all the way. And in my knowledge, the 2 people originally developed the vector differential calculus or differential vector calculus is one is Maxwell, another one is Poincare. Actually, both are equally genius, but many people do not know Poincare because he is more mathematician. Of course, many people even do not know Maxwell. Uh, uh,
So what was the second name you told?
Poincare. I think mm, recently Poincare introduced one conjecture. It states that you take any shape and you just fold it in any manner. For example, you take an apple, you can fold it, you can cut and you can put it in the other way and cut it in the other way. Like that, when you do that within the finite times, not infinite time, within the finite times, when you fold that, it will become sphere. So this is very simple that you take mug and you just keep on bend it like a clay like that. When you bend that, automatically it will one particular time it will come. This is, it look like, yeah, it is correct, but mathematically proving that is very difficult. That is what we have often referred as paradox. So, or conjecture. So that is often referred Poincare conjecture. So you can also type that. Recently, it's been solved by one brilliant Russian mathematician. For that, Clay Institute awarded him 1 million euros, but he said, "I don't want that." The interesting part that actually, if the Poincare conjecture is properly understood, we can even find how this celestial bodies become spherical shape. It may be in some different shape in the beginning, but how it is evolved to spherical shape, so that you can, when you go back in the reverse side to the original state, we can even see where it came from and in what manner it was there, and the kind of things. So that is
Sir,
what.
but sir,
Yes,
so it was already told us that because everything wants to have the most surface area, so that is why they are taking the spherical shape. It was already
yes,
established like this, right, sir?
yes. Yeah. But this theory will help us that how these changes are happening. Like I already said that, yeah, if you take a mug and if you apply Poincare conjecture, it will become sphere. But if you go in the reverse direction, you will find the mug actually. Similarly, if you take a earth from where it has come from, okay, so we know that it has
Yes.
come from sun or something, or when during the formation of sun, it might be created or something like that. So, but everything else, including the galaxies and even the universe itself, black holes, all these things, their properties we can find out of that. So that is a interesting thing. Uh, but I don't know why that professor didn't utilize that money. Uh, that's again a good question. Yeah, so this differential calculus is a very useful one. It is useful in so many fields, and particularly in the field theory, it is largely applied. It is, in fact, the language of the field theory itself. So you will see naturally this differential calculus will come. So whenever there is a change, that change always will be having some direction, which we often refer as projections. So these projections will help us to define the properties of that particular. We can also define the medium as well as the wave. So both can be studied by using this. And this law, most largely, we have three types of things like a line, or we call that as a line change, and surface change, and volumetrical change. That, and line change is always will be defined with three vectorial directions, and the surface you can find that it will be having any one, because the surface will be having the perpendicular as the, so which indirectly we can say that we have multiplied this dy vector and dz vector as a cross product, which result this. So in other words, we have taken the curl of both the changes, and which results this. So whenever there is a field is flowing through that, we can easily calculate what kind of change is happening within this region. Same thing happens to volume, and same coordinate is just changed. So here this row also will come and d5 will come. So that is the interesting thing. And in case of the z direction, this three coordinate systems will come. This will be a little bit more tricky in the spherical coordinate system, but you can easily, you need not to memorize or do anything. Only thing you have to do is you have to constantly practice that, and obviously all these things will naturally will come to your hand, not even in the brain directly. It will be available, which we people used to say it is in my fingertip like that. So that is the meaning. By means of doing that, your hands will be having that memory, which we call as body memory. So that will come by great practice. So the same thing, for example, in the deep night, you are sleeping, but when a mosquito is somewhere else, it is coming and biting, and immediately your hand exactly go and keep it. So that is not because of your brain, because your brain is already sleeping, but your body memory is doing that. So such a practice is required. Uh, so this is about the differential, and the integral also equally important in case of the this electromagnetic field theory, because here only you are going to quantify many of the important properties. For instance, when you are calculating the electric flux, to the potential energy, or potential energy to electric flux, for that you need differential and vector, both integral calculus, both are required. And here the very important thing is there are two important integrals. One is the, of course, line, surface, volume integration. That is the very common ones. But within the line itself, there are two important things. One is line integration, another one is path integration. The path integration is mostly a closed path. So let's say a particular line is starting from A to B, B to C, and C to D, and once again it come back to A. So this is a closed path. So this closed path most probably result zero for some of the fields and non-zero quantities for some of the fields. So, and that decides the nature of that. For example, electric field will give non-zero value, but in case of magnetic field, it will give a zero value. And this particular property often referred as circulation. So that is why we always say that electric field don't have such a circulation property, like that, but magnetic field will be having that. So that decides the, and so for such a closed path integration, we always use this circle inside the integral symbol, and we will do this integration. But when you do the integration in the reverse side from A to D, D to A, and for some of the fields, it will give something completely different value. So that is why actually we can't take this same A to A to D integration is not equal to D to A integration. Can someone say that why it is so? Why this two integrations are
Sir,
not?
because the line and the path is anti-clockwise and clockwise. So both of them will have different results because the cos angle will be different from all for both of them.
Yeah, that is really good. One more thing is there. Yeah, definitely cos angle will be different. And one more thing is also that. Yeah, that is what that will come. I have practiced this, so I know the difference. So this A to B in the, when you do the reverse side, B to A will come. So this itself will give huge difference in the integration. I believe you could understand that. And similar way we can see, yes.
So this is similar to that only, no? So like area under the curve. If we have two functions and we have to find area between those two functions, the this path integral is similar to that one only, right, sir?
Yes, 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 yes.
Okay, sir.
So similar to the line integration, we have called surface integration, often referred as flux integration. So most probably, for instance, if you a charged body is there, let's say a laptop is there, and after you have turned off, some charge is available. So this is actually radiating some kind of electric field outside. So how to find out that? So you have to draw a surface around that, which we refer that as a Gaussian surface. So once the surface is drawn, so you can take one small area, and we know that perpendicular to that we have this n vector. So you will write ds and n vector into this. Let's say the flux. When you multiply that, you will get the total flux. And once the total flux you have calculated, so that will directly will give the flux, total flux out of the flux density, and that is nothing but the total charge available inside that. So this simple study, which will be a little bit tricky in the real measurements, and that is what most of the EMI, the electromagnetic interference, being studied out of that. So when a system is off, it's off. It should not radiate any power or any electromagnetic field such that it will harm the other another mobile phone or something else. It should not do that. So for that, this value, this total flux supposed to be lesser than that of the recommended value. So that recommended recommendations, all these things will be given by this such a laboratory. So did I mention what is the name of the laboratory in India? If people,
So can you repeat?
no, this I already said. Is it this? Yeah. For example, this is some Apple laptop, and this is giving some type of some amount of radiation. This is harming the another mobile phone, let's say Apple phone or something else. So this is not, this should not be done. Okay, so for that, people will say that your laptop is not good because it is radiating this much. So like that, they will certify that. So
Yes, sir. SAR, sir.
yeah, SAR data like that. But who will do that? Which institute will do that? Well, for example, for defense, we have DRDO. For space, we have the ISRO. Similarly, for this type of studies, we have unique institute called Samir Institute. Okay, so like that, actually, we have around some 4 or 5 Samir institutes. One is in Chennai, Mumbai, like that. Most probably, you can find it will be next to the or inside the IITs. It will be available. So this
Sir,
surface,
is the spelling of the Samir like it is SAMEER?
yes, yes.
Okay, sir.
There are also huge amount of opportunities. I think recently there is a advertisement came that they need BTech internship graduates, means BTech graduates for internships like that. I think those who are doing final year project, they can apply for that. Every year they will open. So it is really good for EC. It is only meant for EC students. Uh, So this similarly, we have integral calculus in the volume integration. So whenever you feel difficulty in terms of volume integration, there are some alternate methods like divergence theorem and Stokes theorems are available. You can apply that and you can convert that to surface integration or line integration likewise, and you can easily solve the problem. And so here there are some examples. So as I already mentioned, that this line integration of every segment, when you do that, the segment 1, 1 to 0, 0 to 1, and 1 to 1, this 1 to 1, like that. When you do that in the reverse order, it will give not -6. Something different will come. So you can try out yourself what will happen like that. And if it is equal, then the field is conservative. And another important concept is the tell operator. It is going to tell the change what is happening or the projection of a particular field or often we refer as a gradient. That is nothing but the change what is happening inside that. So this sometimes will happen simultaneously in uh, 3 directions. For example, here you can see this operator, sorry, this vector has uh, in the x direction, here we have only x quantity, but in y direction, we can see that x and z axis, and there is no y quantity. So this kind of fields, when we calculate for a single operator, like only along x direction, y direction, sometimes it will give some different meaning. For that, a simultaneous differentiation supposed to be done. So for that, Maxwell introduced this del operator. This is one of his original contribution. People used to say that Maxwell's equations are written by himself. It is not. All these 4 equations of Maxwell originally written by somebody else, like Ampere, Gauss, and Faraday, like that. So he rewritten that in the form of del operator or integral operator. So that is what his original work. And during that time, he introduced this displacement current. That is one of the creditable work. So according to people like Mary Curie and some other people got 2 times Nobel Prize, but Maxwell will get around some 4 times it seems. Like that, he is that much brilliant, and he might get some extra awards in the mathematics field since he worked in many aspects of vector algebras. Uh, so this del operator is one of the very important one, and it changed its property while we go for different coordinate systems. And that is why this, whenever you choose a particular application, First, the very first thing you have to define the coordinate system. Then the operators will come and play inside that. And the gradient of a scalar is nothing but this del operator will be applied on a particular scalar quantity. Then it results a vector because del itself a vector. So obviously it will produce a vector itself. So this gradient is going to tell about the projection or direction or the maximum rate of change happening inside that particular field. For instance, if there is a potential distribution, let's say I have a semiconductor. So this semiconductor has its own dielectric constant and it has anode and cathode. So you are actually connecting a battery here. So once you have connected, then you will see the potential difference. So the potential is high here. Let's say V max here and V minimum, maybe it is zero like that. So this is once it is defined, then when you apply this operator will result the change which is happening. So this del V will come, which is nothing but the electric field. So this del is also a vector and electric field also a vector. Then you will see the electric field will come into that picture. I think it's supposed to be in the opposite direction so that the current will start to flow. Yeah, I think the first one is correct. This is correct. It's not correct because the electrons will come in the opposite direction. The conventional current is in the forward direction. So this kind of many. Whenever some people are designing a new device, so let's say we are constructing some type of MOSFET or something. This is oxide, this is metal, and this is some kind of heavily doped. Have you studied semiconductor physics, semiconductor devices and circuits in your first year? Th- Anybody else? Anybody else didn't study this semiconductor physics or something? Are you there? Am I
Yes,
audible?
actually, some of us studied, but some of us didn't.
Let's say you can take some semiconductor device. Uh, so once in order to solve, uh, in order to calculate the current actually flowing from here to here, the very first thing you have to calculate the electric field. For that, the first thing or the initial conditions for this boundary value problem is the potential. From that, we will apply this gradient and we will get the electric field. Once the electric field is calculated, then we know that the drift velocity will be calculated. From the drift velocity, drift current and diffusion current, all these things will be calculated. Then by integrating over the length, we will get the total current. So that is a general method. So even recently, there was a big argument that which subject is supposed to be taught first. So whether electronics or some circuit theory like that, there was a debate. And we people who works in electromagnetic field theory, we argued that the electromagnetic field theory is supposed to be taught first because there we introduce all these field components. Then electrons, everything will come next like that. And interestingly, this kind of field theories not require any charge densities to explain the behavior. So it is completely independent of any material. And in case of the electromagnetic field theory, largely it is very useful to quantify the field distribution with respect to the different potential energy. And here some example like if the gradient is applied for a system where the heat, how it is exchanged and how it is reduced. When you, for example, yeah, uh, high temperature liquid uh, is going from, let's say this is the air, and this is actually going from here to here. And these tubes are nothing but some water tubes. So when the air is going from this hot, high temperature air, when it is going from here to here, you could see that here the temperature gradient is very high, and this temperature gradient is keep on decreasing, and it become very low here, so that the hot air become cool air. So this particular phenomena. So we can see that what about the size of this thing supposed to be so that this rate of change will be much faster. And if you want to change the temperature from, let's say, some 50 degrees Celsius to 25 degrees Celsius, what is the length of that tube supposed to be taken? So everything we can easily do it with this uh, calculation of gradient itself. And the gradient has three forms. Even recently in 2015, yeah, in 2015, this paper has come after the release of the movie. So they used inside that they used actually the spherical gradient not to calculate the accelerations inside the black hole, which we call gravity. So this tells how this backside, for example, front side we have this uh, particles are moving, but in the backside also there will be a particle. So those particle we can't see in a normal system. For example, in the Saturn rings, you can't see that backside, but in case of a black hole, it can bend the, for example, in the backside there is a particle, and that particle will be bent and uh, it will be visible as a dot here. So that is what we call gravitational lensing. Uh, this gravitational lensing concept made Einstein famous. This gradient has its own calculus. So when you multiply, when you divide, what will happen for the uh, with respect to the scalar quantity, this these all calculations will be varying. So some examples you can see practice. And yeah, next concept is divergence. So this divergence tells about the same thing like a gradient, but it is telling more about inward outward flow rate or something like that. And most probably it will be done for a closed surface. So if you take a particular charge at the center and you have a closed box or a closed surface you are considering, and that then the field exerted out can be calculated. So using this divergence. So when you take the, uh, mm, so here we can do the divergence only for a vectorial quantity. And therefore, if you do divergence of a scalar, it is completely meaningless. For example, this is more suitable for electric field. And there also we have calculus. So you can see by yourself. And what divergence theorem says that if you feel difficulty of doing yes surface integration, I'm sorry, yeah. If you do a surface integration, instead of that, you can take the divergence of the particular operator and do volume integration. So this is purely depends on the complexity of that. If you feel that this surface integration itself is easy, you can do that because you have to do for the entire all. For example, if you have this cube, then you have to do for six surfaces are there. For six surface, you have to do the integration. But if you can handle this whole integration, volume integration by single hand, then you can do that. So it is purely your so we will also see that how this divergence theorem evolved originally, which is developed by this Gauss. So that is often referred as Gauss divergence theorem. And there are some examples you can see here. And the next one is curl. Curl is nothing but whenever the operator is having the rotational property, which I said about the circulation property. So with respect to a particular point, the field will be in the circular form, in a closed form, like magnetic field, how it is closed. So for those, we have to do this cross product of the del operator, so which often referred as curl. So curl of a magnetic field, curl of a magnetic flux, like that actually you will see that. And this is very, very useful one in order to see what about the field components around a particular line or around a particular body, how it is. So in order to do that, we always supposed to take a path. That path often referred as Amperian path. We will see these all calculations much more in detail in the future class. And for this del operator, we supposed to use this matrix form, and the matrix form we have to calculate the determinant of that, and that makes this calculations a little bit tricky. So this also will come by proper uh, handful of practice. And the interesting part is some of the you don't worry about that, many of the vectors will be zero in some of the field components, like if a field is available only in the xy plane, not in the z plane, so obviously that operator will become 0, then naturally the calculations will be much more simple. There also calculus are available. You can go ahead with that. So you can clearly see that when there is a vector, let's say this is a magnetic field. So around this is the transmission line or something else. So when the current is flowing, we get the yeah, magnetic field, just it will be around that. So in order to calculate the magnetic field around that, we have to take the Amperian path, and just we have to do some calculations. So you can easily find what is the current flowing inside that. So because we are simply doing that. So this later named with the del cross H equal to J. J is nothing but the di by dx, that's, which is nothing but the current density. So this is applicable only to curl, but in case of the curl for electric field will always go in a particular direction. So it will be zero curl like that. So electric field don't have this circulation or curling property. And you can apply Stokes theorem to simplify the calculations. Multiple calculations you can work out, and there are multiple places you will see that the second derivatives of the del operator will come, like when you do the gradient of divergence of like that, or gradient of curl of like that will come. So sometimes this operator will be meaningful, sometimes this operator is completely meaningless. For example, the curl of a divergence is a meaningless one because it always results 0. And similarly, this curl of curl will always give only a single vector which is perpendicular to the vector as well as the del operator. So this curl of curl supposed to be done in the surface level, not in the volumetric level like that. Many arguments will be there. So we will see. So it will vary with respect to application to application. So that we will, when we really take the operator, will form. So this directly will give many important operators like semiconductor physics, as well as, for example, when we design a microwave oven, this del operator will come, because where the boundary will be defined, obviously boundary value problem need to be solved with Laplace theorem only. There this second derivatives will come. So that is going to tell whether this chicken will be fried or not, or the water. If you put a water, sometimes you can notice that if it is a salty water, there won't be any change. Water will be still chill only inside that. So there are many interesting properties we can study out of that Laplacian. And one more thing, we will see Poisson equations will come out of that. So these are the mathematics so far now. We haven't studied in detail, not even with any hands-on experience. But I recommend you to go for this. So before coming to next week, you have about 3 days you have. So each day you take one. One day you take vector, another day you take uh, coordinate system, all these things. Uh, so I'm not sure about your habit about studies and all the way. Some people will study at the last day, or sometimes even they will study after the exam also. Um, so I'm not sure about that all good habits, but if you practice this by proper way in daily basis, all the courses you touch all the day almost like that. At least before going to bed, you have to take the book and go one time, see the pages of today's whatever that been taught. At least note down the page number, something like that. So daily basis you have to talk out. Then you will understand slowly, and you will feel the entire semester will be meaningful. And now I'm going to talk about your the opportunity itself a little bit more in detail.